So from here, we're going to get more into some of the important properties as well as the reactions that these unsaturated compounds undergo. Now, for the most part in this area, we're going to focus on the reactions of alkenes. And the reason that we focus in that area is that alkenes are, fairly important in a number of different contexts. And we'll see some of those examples as we go. And there are a lot of biochemical examples where we see alkenes, as well as many other important classes of compounds. When it comes to alkynes, though, alkynes are a very different story. We don't find a lot of alkynes in nature. We don't see them a lot biologically. And so what we'll say is that alkynes react in a lot of similar ways to alkenes. There's a lot of similarities in what they can do and in many cases do, but we won't specifically get into their reactions. But the first property of alkenes I'd like to talk about are to talk about briefly a class of molecules known as terpenes. Terpenes are based on isoprene. So isoprene is this 5-carbon diene that its structure is drawn here. Now, a terpene is any compound whose carbon skeleton, its carbon backbone, can be broken into 2 or more isoprene units. Now, it's important to note that when we end up talking about isoprenes themselves, it's the carbon skeleton, this shape of 5 carbons like this, that matters, but not necessarily the actual alkenes. So many molecules that are considered terpenes will have repeats of this 5-carbon group, shaped exactly the way we have it here, but won't necessarily have the alkenes. And the reason we bring up terpenes is we find them in a lot of familiar places. So this molecule, for example, is menthol. And while the alcohol itself isn't part of the terpene, we have one isoprene unit here, and one there. And so menthol is just basically these 2 isoprene units that are stuck together. We can also see the same thing in a molecule here, such as geraniol. This is a compound that's responsible for a lot of the fragrance that we get from roses. And again, you can see that we've got these 2 terpene units put together. These 2 isoprene units put together. In this case, we do have some alkenes, but still, the entire carbon skeleton of this molecule is these isoprene units. And it can be as simple as these molecules like menthol or geraniol, which are just 2 isoprenes put together. Or we can have a very complicated molecule that's a whole bunch of isoprenes. So this you might recognize as beta-carotene. And if we look carefully at the structure of beta-carotene, it's all just these isoprene units put together. So we went a little far, too far over with this purple one here, so let's fix that. And so there you can see beta-carotene is just 1, 2, 3, 8 isoprene units put together. Alright, so what do alkenes do? Or what can we do with alkenes? So this is where we start looking at reactions. And unlike alkanes, every other functional group actually does a lot. There are a lot of different reactions that we find for alkenes. Now, most reactions of alkenes are what we would call addition reactions. Addition reactions are exactly what they sound like. We take a compound such as this alkene, and we add something to it, and they add together to form just a single product. And so that's a typical example of an addition reaction. And most addition reactions, especially for alkenes, we find are highly favorable on the basis of energy differences between starting materials and products. Now, what are A and B? What can function as A and B here? Well, the answer is a number of different things. And the first one we're going to look at is the addition of HX. And remember that when we use the letter X to abbreviate, the letter X generally stands for just some generic halogen. So we can take our alkene, and we add HBr to it. The HBr is our A and B, if you think about the way we had it on the previous slide. And so as a result, the hydrogen gets added to one carbon, and the bromine to the other carbon. We also see that the pi alkenes are no longer there, or the electrons of the double bond are no longer there. And then the bond that was between the hydrogen and bromine is also gone. Now, as we start to learn more reactions, the molecules, the starting materials that we look at, will have the ability to get more and more complicated. And so it's really important to focus on the functional group. So, for example, we're learning, this is our first real reaction that we're learning. It's the reaction of HX, which could be HBr, HCl, and so on. But it's the reaction of HX with an alkene. So it doesn't matter whether your alkene is as simple as this one, or much more complicated like this one is. The overall idea isn't going to change. It's the alkene, it's that functional group that's going to react. What happens to the rest of the molecule? Well, it's not affected. It just comes along for the ride. So what would the products be in each case? Well, this first one, again, pretty straightforward. We only have 2 carbons. One gets the hydrogen, one gets the bromine. Now, do I need to keep drawing this hydrogen in? We know that we don't. We know that hydrogens are always implied. The only reason that I keep drawing it in is so that you're seeing that addition. That's specifically the hydrogen from the HBr. What's the product from this much larger, more complicated molecule? Again, that double bond goes away, hydrogen and bromine. Now, these first couple examples we've done, the alkenes have been symmetric, or at least very close to being symmetric. What happens if the alkene is not symmetric? And it doesn't take a lot to get us there. I mean, even a molecule as simple as that one is no longer symmetric. So does the H go here and the bromine here, or bromine here and hydrogen here? Well, so the true answer to this question is it's actually both a not terribly difficult question to answer, as well as being a very, very complicated question to answer. So unfortunately in this course, we don't get into what we call reaction mechanisms. And that's just a matter of time. Reaction mechanisms take a lot more time than we have because we only have 1 semester to get through organic chemistry, as opposed to in the class where I would teach mechanisms, we have 2 semesters to get through all of this. Reaction mechanisms are the step-by-step pathway that show us how the bonds break and how the bonds form in a chemical reaction. In other words, what we're saying is that if you look at this reaction we have on the screen here, it doesn't just happen all at once. We don't just get all at once everything comes together and gives us our product. There are certainly reactions where that does happen, but this is not one of those. In fact, in this reaction, the mechanism is actually 2 steps. But again, we don't do mechanisms in this course just because of lack of time. But there are going to be times where if you ask that question, how do we know, how something happens that way? It's because people have studied the mechanism of the reaction, and the reaction mechanism gives us that information. For a lot of the reactions that we study, we're just going to sort of go right to the answer and sort of accept the answer that the mechanism gives us. And so for a reaction like this, we have something that's known as Markovnikov's rule. Markovnikov's rule says that for the addition of HX to an alkene, the hydrogen goes to the carbon with more hydrogens, and X goes to the carbon with more carbons. So how does that apply to this example? Well, let's put in all the hydrogens so that we can see. So the hydrogen is going to go to the carbon with more hydrogens, and we always have two choices. That's this yellow carbon and the green carbon. The other carbon, the CH3, doesn't factor in because it's not part of the alkene. The green carbon, we can see, has two hydrogens, whereas the yellow one has only one hydrogen. So Markovnikov's rule says the hydrogen is going to go over here onto the green carbon. At the same time, Markovnikov's rule tells us the bromine goes to the carbon with more carbons. The green carbon is bonded to one carbon, whereas the yellow carbon is bonded to two carbons. And so our bromine goes here. So this is an example of a reaction where, at least in theory or based on the definition of what an addition reaction is, it could give multiple isomers as the product, but it prefers to give one of them. And these examples we've done so far have been with HBr, but we could have just as easily done this with HCl, or HF, or HI. And all of them will do the same thing. Hydrogen to the carbon with more hydrogens, and the halogen goes to the carbon with more carbons. Before we get to the next reaction, one last thing that I want to remind us of, and that's that aromatic rings are not alkenes. So if you were presented with a question like this, benzene plus HBr, aromatic rings won't react with HBr. They actually need much stronger reactants. And so what would happen here? Nothing at all.